Hello, I'm Vincent Rooyakkers, and this is Lab 1, Constant Velocity. This lab tasks us to film an object moving at a constant velocity. I feel there are several goals this lab hopes to achieve. First is observing objects moving at a constant velocity and analyzing the factors that come into play in order to achieve this. For example, we applied an impulse at the beginning by pushing the ball, and then the ball gradually rolled to a stop at the end. So we had to analyze the footage for a point in between where it appeared the ball was moving at a constant velocity. The second goal is to demonstrate the difference between computer models of constant velocity and constant velocity in reality. As in the real world, it is very difficult to get an object to move at a constant velocity as the net forces acting on the object have to sum to zero, which goes into the third objective of applying Newton's second law. This was used as we needed to find a point where the object's acceleration was equal to zero, and this would be where the net forces was equal to zero, as the net force is proportional to the object's acceleration. In this lab, I used a golf ball and a glass table. Here is my observed motion and tracker. At this point, I found the force of friction was about the same as the remaining force of my push. The current orientation of my axis is important, since velocity is a vector and direction is a factor in this. Although the speed would be the same, my resultant position and velocity vectors would be negative. Looking at our tracker results, we take the final position and subtract the initial position of the ball and divide it by the change in time to get our velocity for the computer model, as we are assuming a constant velocity at this point. Doing so gives us a velocity of 0.14754 meters per second. Since our camera is 30 frames per second, each data point is 1/30th of a second, which is our delta t. Another important factor to consider for the computer model is how velocity is not changing despite updating it with acceleration, and this is due to the net force being zero, so there is no acceleration. This model will not be accurate to the results obtained by tracker, as it is very unlikely that there is no acceleration captured in that clip. Now observe the computer model results. Notice the linear line. This indicates there is no acceleration, as that would cause the position graph to curve. Now let's compare this to our tracker data. Notice how the r squared for the tracker is not 1 like it is for the model. This implies that there was some change in velocity for my observations. This could be friction acting on the object, drag, or maybe even the ball didn't roll in a perfectly straight line, causing a slight change in direction. All this would involve acceleration, which would not imply net force was equal to zero. Is it possible to figure out what is needed to find if net force is equal to zero? We do know that the force of the table pushing on the ball has to equal the weight force, as it would either float away or fall through the table. For the horizontal components, I would assume drag would be negligible, as the ball is small and slow moving. This would mean that the force of friction would have to equal the force of the push. For mine, I feel that the friction was slightly greater, as the curve for the tracker's data curved slightly inward at the end, indicating either a negative acceleration or force acting in the opposite direction. Thanks for watching.